Good morning, my name is Elijah Ford from Fraser High School, and together with Noah Pashby, also from Fraser High School, we will be presenting to you the AP Physics movie presentation, Interstellar Edition. Let us first begin by viewing a clip.
Thrusters.
Ready?
Ready?
Ready.
Main engine ignition in 3, 2, 1. Mark. Lander 1 engines on my mark. 3, 2, 1. Mark. Ranger 2 engines on my mark. 3, 2, 1. Mark.
Well, this whole maneuver is gonna cost us 51 years.
You don't sound so bad for pushing 120.
Now that we have found the kinetic energy of the Endurance, we must find the gravitational potential energy between our two bodies, the supermassive black hole and the Endurance. If you guys recall from the applications of the law of gravity, work done by the gravitational force is equal to the integral of this force. Also, if you guys recall, the change in potential energy is equal to negative work done. So by negating the integral of our gravitational force, we are left with negative big G times big M times little m over R. G, which is our gravitational constant, is equal to 6.67 times 10 to the negative 11th. Big M, which is equal to the mass of the supermassive black hole, is 1.989 times 10 to the 38th. And M, and little m, which is representative of the mass of the Endurance, is negligible in this case due to its relatively small mass compared to that of Gargantua. This leaves us with one unaccounted for variable, which is R, or the distance between the centers of our two masses. So how can we find R? Turns out that this is actually an answerable question. If you recall from the clip, the Endurance moves along the event horizon of Gargantua. The event horizon, also called the
Schwarzschild radius,
can be determined by the formula 2 times gm over c squared, where c is equal to the speed of light at 2.99 times 10 to the 8th meters per second, m is equal to the mass of Gargantua at 1.989 times 10 to the 38th kg, and g is equal to our gravitational constant at 6.67 times 10 to the negative 11th. By using these variables, we can find r at 2.95 times 10 to the 11th meters.
Now that we've found the radius, we can find the gravitational potential energy between the black hole and the spaceship. Since the mass of the spaceship is negligible compared to the mass of the black hole, our equation gets reduced down to negative gm over r, where g is our universal gravitational constant, m is the mass of the black hole, and r is the Schwarzschild radius. This leaves us with an answer of negative 4.49 times 10 to the 16th joules of potential energy. Now, what can we do with this result? We can compare the kinetic energy and the potential energy, and that will help us determine the kind of orbit or trajectory the spaceship will have around the black hole. If the kinetic energy, the difference between the kinetic energy and potential energy is less than 0, or the potential energy is greater than the kinetic energy, it will have an elliptical orbit and will not escape the black hole. If the difference between kinetic and potential energy is greater than 0, or it has more kinetic energy than potential, it will have a hyperbolic trajectory, exiting very quickly. And if the difference is 0, or the kinetic energy is equal to the potential energy, then it will have a parabolic trajectory. One of the interesting qualities of a parabolic trajectory is that it is always moving at the escape velocity. Now for some calculations. The sum of the kinetic energy and the difference between that and the potential energy ends up being 8.31 times 10 to the 16th, which is much greater than 0, leaving us with a hyperbolic trajectory, meaning it will escape the black hole's gravity very quickly.
Thank you for watching. Are there any questions?
Radius.